average rate of change related to a secant line? They're the same thing. How is instantaneous rate of change related to a tangent line? They're the same thing. What can we at this moment actually find a limit? No. What can we do though? By doing what? Making the interval smaller. So as we get closer to the y value, then we're doing that by shrinking up the x to a interval. Is that okay? How is let's do this one. What? Oh yeah, we'll do that here in a second. How is it? How's that read? So what is L? What is L? A y value. Yeah. Okay. Good. So then 41. Okay. A function f is even. If that's true for all x in the domain of f, if f is even, with the limit coming from the right going to 5, and the limit from the left going to 8. Okay, so then the limit, 1, 2, 3, oh, here, let me get this better. Because right, we're going to 2, is that right? Do we need the negative sign? Oh, okay, yeah, for negative 2. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. So from the right, because we're going to negative 2, right? So from the right, it's what? 5. So like this, and then from the left, it's 8.
Well, I think it's telling you if we're going to attack approaching positive 2, you have to find it for negative 2.
Oh, they're telling us positive. Okay, sorry. So all the information is from positive 2?
Yeah.
Okay. All right, so then from the right, it's at 5, 1, 2, 3, 4, 5. And then from the left, it's at 8. Okay. Okay, so then we're coming at negative 2. So what? Since it's even, what's it going to look like on the other side of the? It's going to be reflected, right? So then it's going to look like this. Is that right? So then they're asking, so if this is true, if it's coming from the right at negative 2, what is it going to be? 8. And then it's coming from the left to negative 2, it should be 5 then. So is that, so okay, so if you did that without drawing it, like it's confusing, right? Like why is it switching? But if you draw it, then it's, I think it makes a little more sense as long as you understand it's reflected. So, that's why we want to be looking at our graphs and things like that. Is that okay? All right, anything else from the homework? 39. Uh-oh, I haven't done 39 in a long time. Assume the postage for sending a first class letter in the United States is 44 cents. Up to including, okay, and 17 cents for each additional ounce, up to including that ounce. Graph the function, okay. All right, what's our x and y axis going to be? What is? All right, so 1 ounce, 2 ounce, 3 ounce, right? And then, so then what's the first one that makes sense to put on here? 44 cents, and then what's the next one? And then, I think that should be good enough. And so 44 cents, even if it's barely any weight at all, up to including. And then right then it jumps like this. Is this okay? So it's very similar to 37. Does that part make sense? Evaluate, what was that, 3.3. So when I say evaluate, what do we need to be doing? Oh, I guess I need one more first to do it. All right, it's going to look like this. What's 17 plus 78? So, okay, you should be answering something very specific about how we should be doing this, because we're going to 3.3, that's our A, right? So, what's the limit? How about that? So this is part B. What is it? Well, you can just tell me the actual answer if you know it. $0.95. Why can we say that though? This is like a theorem. Okay, so in your mind, if you want to think like Bryant does, that's fine. He's saying it's in the middle of the line. It's like right there, right? But math-wise, what we have to say is that this is only true if both coming from the right and the left give us the same thing. And right, we're talking about very, very, very close. So both from the left and right are giving us 95 cents. Is that okay? So make sure you're referencing this information. Okay, again, that's how you get, you know, a bunch of people are saying, I want a 4 and I want a 5 and things like that. Then you need to be referencing these theorems. It works because I have to come from the left and the right. If you don't memorize the name, make sure you can describe the theorem itself. Right, that's theorem 2.1. All right, interpret the meaning of right and left at 1. Okay, so as we're coming from the right, as we come this way, what is the limit at x equals 1 from the right? Focus. It's 0.61, right? 61 cents. We're up here, getting closer. 61 cents. What about from the left? 0.44. Okay, so what does that tell you? Oh, what can that tell you about just the limit? This isn't part of your question, but yeah. Okay, so the limit at 1 does not exist. Does the limit at 4 exist? No, because it's going to keep repeating this as we go, right? Is that okay? All right, wonderful. Anything else from that work? Cool. All right. I hope you guys know it. I hope you guys know it. Let's get to page 76 for a second. All right, so now we're moving away from just kind of getting a feel for it, what limits are. And again, limits are going to come, and we're going to use limits this whole chapter, but everything in this book is based on limits, okay? So we will get away from limits for a while, but they'll keep popping up as we go through. And so we got to keep them in mind as we go. The other thing to keep in mind, and you know, one of the coolest math classes I took in college was actually just a geometry class, and they started us off with 3 definitions of a point, a line, and I think the third one was opposite sides or something like that. And from there, we built the whole geometry. We used those three definitions, and we came up with our theorems, and we came up with everything. And that's kind of how you want to look at this book. We have an idea of what the limit is right now, or a calculus, I guess, not just this book. But we have an idea of the limit now, so what can we build off of that? So if we're looking down here at the bottom of 76, they talk about limits of linear functions. And think of a linear function, right? We're just talking about lines, and you know what? We don't even need to read it. What do you know? Like, firstly, like what kind of situations when we're dealing with limits throws us off? Holes. Yep. What else? Lines that don't meet, and then there could be one other one. We haven't really super talked about it, but what are those? Rational functions, right? Those are the three things, because like sometimes rational numbers, they have a hole or they have the asymptotes, right? So those are our three issues. Do linear functions have any of those issues? No, they don't. So again, we are starting to evaluate limits now. So can someone make some kind of statement about a linear function? Like, something like super easy, like just y equals x or f of x equals x. And we'll look just in this first quadrant. So, I didn't hear the whole thing. What did you say?
So, for any given point or any given value that is approaching the limit, it's always going to just be m.
Not just m, because remember the limit is the y value. You're on the right track, though. Right, because it's always f of x. So, right, so if we approach from both sides to 1, it's just whatever's there. And from 2, whatever's there. Does that hold for every single linear function? So basically what he's saying is, this is basically what he said. The limit, as x approaches Ra of f of x is just f of a. Does that? Okay.
So would the instantaneous velocity always be at m?
So, yes, correct. So, one of the reasons that the book is suggesting that we kind of put that aside for a little bit is so that you're not getting mixed up. But yeah, the instantaneous velocity on any linear, for any point on a linear function is just going to be the slope. Yep. Because it doesn't change, right? It's constantly increasing or decreasing at that rate. So yeah. So does this make sense? Okay, so then, like if you look up at the top of 77, we've got a new theorem, right? Theorem 2.2, limits of linear functions. Let a, b, and m be real numbers for this linear function, f of x equals mx plus b. And then they just wrote basically what we just said, right? And they added a little bit, right? Because it's... So what does that tell you about how to evaluate any linear function? You just plug it in. Is that okay? All right, so then now we can introduce these limit laws. And so we got 7 of them. But let's look through them together. We're going to go kind of quick. Right, any two functions added together, if you're asked to take the limit of that, you can actually take the limit of each part and then add them together. Right, same with the difference. If you have any kind of subtraction inside of your function, you can separate them, take the limit of each part, and then subtract them afterwards. Okay, and that goes with the constant, product, quotient, power. 6 and 7, they actually, in a couple pages, will define more. So you're allowed to play around with these functions. Is that okay? So anyone got anything right now that they're worried about these limit laws? Okay, cool. So then let's flip over to the next page, and they kind of apply those limit laws. I think I'm going to guess that you guys are okay with those. Is that true? Yeah. And before you answer, let's look down here. They say limits of polynomial and rational functions. And so then they work through this little polynomial. And so you may not have understood that you could do this right away from those limit laws, but look what they're doing down here, and I'm going to explain why they're doing that here in a second, if I can get it on there. Right? Here's a polynomial, and all they're doing is breaking it down. So like each of these terms are just like a separate function, right? So any giant function that you have, you can break it into individual terms if that's what you want to do. And so if you're looking through here, they apply law 1, 3, and 6. But basically what they're doing with that is making them into linear functions. Because we just agreed, and we have a theorem that says if they're a linear function, then that means we can just direct substitute into them. And then what we did was take this somewhat more complicated function and break them down through these laws and made them just little linear functions. And then we squared when we needed to, we added when we needed to, multiply by a number when we needed to.
We don't have to break it down all the way like they did, do we?
Okay, so to answer this question, no, you do not. And can you explain why you don't have to break it down?
Just because you can solve it from one of those points.
So then how do you find the limit of a polynomial function then?
I would split it apart. So that's very simple. Split them apart just to know my first one. So,
Well, but you just said that you don't have to, so before we go on.
how it is.
Yeah, okay, so the whole point of us looking at this is that we're building mathematics. We're all happy with saying that a linear function is just direct substitution. And now we just show that polynomials are just a bunch of linear functions thrown together. So then a polynomial, the limit of a polynomial can be found by just direct substitution also. Is that okay? Do you see how that works? So then if you're asked to find the limit of a polynomial, you can break it up like this if it helps you. Or you can just say, I'm plugging it in. Because I know these are all just a bunch of linear functions, slammed together and squared and cubed and stuff like that. And by my limit laws, I know I can play around with it like that.
So you were just trying to find like the limited type of approach like 5. You can just plug 5 in.
So we could just go straight to here, right to the stop thing, and just plug 5 into everything, and that's going to be the same as if you broke it all the way down.
And is that ever going to change? Like, is there ever going to be a point where it's not the same if you did break it all the way down? Like, is it always going to be like before it's broken down, it's basically like the same things afterwards, or is it going to be like sometimes when you break it down, like it changes how you plug it in?
Are we talking about a polynomial function?
Yeah.
Then we can always do this. Okay? Now, they may play around with it and throw a bunch of polynomial ones together. And there is something, and if you look up to the top on page 79 in the little sidebar thing, basically it's going to answer your question, right? The condition under which direct substitution can be used to evaluate a limit become clear in section 2.6 when we talk about continuity. Okay, but as of right now, just your normal polynomial, yeah, you just totally just plug it in and you never have to worry about it.
Do we always have to reduce it so much? Like, can't we just do like law 1 or law 3? Like, where do we have to do it all?
So again, no, you do not have to do any of them, really, if you're asked to evaluate a limit. This is showing that the whole idea is that, like, we took this one thing that we all agreed on, which was that a linear function, the limit of any x value on a linear function is just plugging in that x value. And now we're expanding that to say, hey, look, then that's going to make it true for polynomials. And that's what our next theorem is up at the top. A polynomial function is just plugging it in because of all this. So then you don't really have to do it anymore, but you do want to understand why that's okay. Is that okay? And then I gotta say, oh look, rational functions are just a polynomial over a polynomial. So then that means for a rational function, we can just plug in any value we want to. Okay? Now there's a little caveat, or however you say that, right there. It says, the denominator, if you plug in a value, it can't be 0 because you can't divide by 0. Okay? So what that means is so far we have right, we have this situation where a linear function, defining the limit of any value for a linear function, plug it in. Any polynomial, plug it in. Rational function, plug it in. Is that okay? This is going to take more time than I want. I want to do more today, but you guys got time, so you can do it later. All right, so, well, all right, so here's how we're going to do it. You guys are going to have to do a little bit of work. So, one-sided limits, right, are down at the bottom of this page. And basically what it's going to say on the next theorem, basically it's going to say is one-sided limits are treated exactly like limits. Okay, so if you're coming from the right, you can just plug in that number. If you're coming from the left, you just plug in that number. But then you flip it over, and then theorem 2.3 says, oh, by the way, be careful when you're dealing with rationals. Okay, like you can't come from the left of a square root if it's at 0. Okay, is that okay? All right, so we got time. Your homework is up to 38. So, oh shoot, we didn't do the one thing. So you're doing 11 to 38. Did we do 1 to 7 on page 1 to 6 on page 72? Did we go over those? We did not, did we? Yeah, well, it's 11 to 38. Did we do 1 to 6 on page 72? Did we talk about those? All right, let's do that. I want to do that. All right, so number 1, I always want to do that. I was rushing because I wanted you guys to take your pop quiz today, but you'll take it on your own time. So explain the meaning of the limit, of that statement. You guys can already did that, but say it again. What's the meaning of that statement on number 1? All right, the y values approach the value L. Good. Number 2, true or false? When the limit as x approaches a of f of x exists, it always equals f of a.
No, not always.
Not always, right? That's the situation where you have a hole and then the dot above it or below it or something like that. Okay, so false. Explain the meaning of that.
As it actually, as it approaches a from the positive side.
All right, so from the positive side, okay. And then number 4. All right, from the left side, okay. Number 5, this is a good one. If approaching from the left side it gets to L, and then from the right side it gets to M, where L and M are finite real numbers, how are L and M related if the limit exists there? They're the same number, good. What are the potential problems for using graphing utility? This is like a question for Matt. Yeah, you might not be able to see it, right? Some of the newer ones show you that hole, but some of the older ones don't. Okay, so just be careful. All right, so on the AP College Board website, you guys got time to do it because you only get 16 minutes and it shuts you down. You got to do this before I see you tomorrow, so doing it now would be a good idea, right? 16 minutes, there's 8 questions, that's 2 minutes a question. It's multiple choice. Okay, so you don't need a calculator for this. You can have one out if you want. Yeah, you can close your book. If you're you should have time to do it. So unless you can't get on by 9 o'clock, then you can do it now, and you might as well just do it now. Because once you press start, 16 minutes, you're on the clock. Otherwise, if you're not going to do it now and you don't feel like you got enough time, then go ahead and start on the homework. And like I said, make sure that's done before you come and see me tomorrow. Also, if we have to go hybrid, we have to meet every day. Okay, so whether you're in the building or not, you have to get on because we don't have that kind of time. Okay, so yeah, it should be an assignment. It should be pretty easy to find, I think. And I hope it's good on the phones, I don't know. Yeah, okay. All right, yep, once you get on, 16 minutes.
How many questions are there?
8. You get 2 minutes left. Right, once you start, the clock starts 16 minutes.